particularly after such a magnificent first day. That was a fantastic set of talks and discussions we had yesterday. So what I'd like to do is build on all that terrific knowledge, information, and insights we had yesterday, and talk a little bit about all of this from an Earth system perspective. I think it's important to understand that, to understand what the Anthropocene actually means and where we might be going with it. So my talk's going to be in 3 parts. I'll give you a very quick 5 to 7 minute primer on Earth system science. Then we'll talk a little bit about the human dimensions of the Anthropocene. There are many more people in this audience who are more expert on this than I am. But in particular, I want to put the human dimensions in an Earth system perspective, because after all, we are part and parcel of the Earth system. And then lastly, I want to talk about this question, where are we really headed the rest of this century and beyond? But I'll do it again with the lens of an Earth system scientist. So the first thing I want to make is a simple statement, but it actually is quite a profound one. The Earth that we see here is a single system. Notice that we use the singular form of system, not systems. So the Earth is a single system with its own emergent inherent properties at the level of the planet as a whole. And that's really important because we need to interpret what's happening with the Anthropocene from this as well as many other points of view. And to do this, we need to go back in time, not nearly as far back in time as we went yesterday, with David's wonderful talk on big history. So I'll only go back maybe 50 to 60 million years, which is sort of the blink of the eye in terms of the history of Earth and the universe. But the important point there is we see states of the Earth system that are quite different from the one we're in now. We can see states all the way up to here which were basically ice-free. Antarctic ice didn't start forming until this cooling event here about 34 million years or so ago. And then from about the start of the Miocene on, you see a very, very, very gradual cooling until we get into this really interesting period, which is the period of hominids. And this is the one I want to focus on today from an Earth system point of view. This period of oscillations, quite radical oscillations in a way between cold and warm, and a very regular periodicity, which is part and parcel of being an Earth system. So to study this more, we'll go back to where Tom Griffiths took us yesterday, which is Antarctica. This is Australian Antarctic territory, and as Tom showed, we can go out there, do some very interesting research out on top of that very big ice sheet. And the most interesting from our point of view as an Earth system scientist is that we can drill down into the ice, pull out the cores that Tom showed yesterday, and really dig out some beautifully layered information back in time, not only about the climate, but about the composition of the atmosphere, gases, dust, other particles, and so on. Fascinating stuff. This next one here is probably the most iconic of the Antarctic ice cores, one of the first ones that came out in '99, the so-called Vostok core. I'll refer to this later in my talk, but for now, all I want to do is focus on the middle of the lines here, the red one, and that's a proxy for temperature on Antarctica. There's a temperature scale here. But the point I want to make from an Earth system point of view is you can see really nicely how the Earth exists in 2 different states. There are glacial states here. I've only circled 2 of them, but you see 2 more back here. And then you have rather shorter intervening interglacial or warm states. So this, in the last 500 million years, operates with about 100,000 year periodicity. In fact, that goes back about 1 million years. Before that, it was about a 40,000 year periodicity. But the point being is that the Earth spends most of its time in this rather erratic, very cold state with large polar ice sheets, and these intervening warm periods are rather shorter until we get to this one, and I'll talk obviously about this one in more detail. This one is what the paleoscientist community call the Holocene, the present accepted epoch in Earth's history. But the point is, from an Earth system point of view, we exist in 2 fundamental states in the late Quaternary with very regular patterns of oscillations between them. Now, what I want to do is again, start bringing humans in, because this ice core encompasses the entire period that fully modern humans have been on the planet. So we evolved, I think as people noted yesterday, somewhere around 200, maybe 250,000 years ago in Africa. So this ice core encompasses the entire time that we've been on planet Earth. So when you look at the environments we've gone through basically 2 cycles of ice ages and warm periods. The interesting point is For this entire time, until very recently, we've been hunter-gatherer societies only, no matter where we've been on the planet. It's only this last relatively longer warm period, the Holocene, that has allowed us to develop agriculture. So immediately we see now a connection between the dynamics of the Earth system and human development. And we're going to look at this now in a little bit more detail. So what we'll do is look at the last 100,000 years, and I'm going to do a bit of a trick here. I'm going to flip hemispheres. This is no longer a southern hemisphere ice core. This actually comes from Greenland. And one of the interesting things you see in Greenland is that rather wild oscillations during the last ice age. They were centered in the North Atlantic, so they're very pronounced in Greenland. You see them elsewhere in other ice cores, but somewhat muted. The point is, it was a pretty rocky road for humanity, no matter where we were during that ice age. Again, you can map on human development here. There's a beautiful synthesis of this by Stephen Oppenheimer, who uses a variety of pieces of evidence to infer how humans moved out of Africa and around the planet. One of the interesting things is most of the major migrations obviously occurred during an ice age. Why? Obviously, sea level is 120 meters lower than it is today. And a lot of places that are separated by water are connected during this period. Nevertheless, of course, the first long migration ended up here in this continent, and that did require some seafaring, which was quite an innovative development for humanity. But again, let's focus here. This is the last little bit more than 10,000 year period, and you can see how steady the climate is compared to what went before. Of course, it's not entirely steady. As we know here in Australia, we've got a lot of natural variability. But compared to what was before, it's a pretty even, steady climate. This is what allowed the development of agriculture. It appeared about 10,000 years ago simultaneously in 4 or 5 places around the planet, led the development of villages, cities, civilizations, and so on. So a lot of what we talk about now in terms of the Anthropocene is referenced against the Holocene and how we're moving out of the Holocene and what that might mean for humanity. So the question is, what now is happening to this Holocene state of the Earth system? That was a hot topic for us in IGBP when I was director back in 1998 to 2000 to 2004. Very interesting time in that program. So we did a synthesis that we published in 2004 of 10 years of IGBP research. And we had all sorts of data about how the Earth was being changed by humans, how it compared to natural variability, and so on. But what we really wanted to do is systematize this. So we came up with the idea that we should produce a series of graphs about how humanity is changing and a series of graphs of how the Earth system is changing. We started at 1750 to pick up the beginning of the Industrial Revolution and went to 2000, which was the most recent date. At that time, we had a lot of data. Now, one of the things that struck us that we didn't quite expect was this year, 1950. And Jan referred to that yesterday. I'll talk a bit more about that. We've now updated those graphs in 2015, so we've taken the data out to 2010, and those are the graphs I'll show you just now. You've seen these before, so I won't belabor them. This just shows how what we call the human enterprise has changed from 1750. We have indicators of population, economy, energy, resource use, connectivity. And again, you can see quite clearly the date 1950 standing out. And these graphs were the foundation for the first use of the term the Great Acceleration, which actually came out of a conference in 2005. Now, one of the innovations we did, and I'm going to come back to this, is this comment from a lot of people on the human dimension side that we miss a big point when we put just human aggregated pressure on the planet, that it's quite uneven across human societies. So the equity issue plays in quite strongly here. So what we've done on these graphs are separated out countries by 3 different types. Those of us in the wealthy OECD countries, the rapidly emerging economies like India, China, Russia, and so on, and the others, which are generally the poorer countries, up here at the top. Now you can see that there's a quite interesting pattern that's not identical in all of these different aspects of the human pressure. So I'm going to go back to that in more detail now, but I just want to introduce it at this point. The thing we were interested in back in the year around 2000, 2002, and so on, was exactly this graph. And this is part of the data that motivated Paul Crutzen to suggest that we had gone out of the Holocene. Because we tracked here from 1750 all sorts of indicators of the Earth system. We have greenhouse gases, we have the climate, we have the ozone, we have the structure and biogeochemistry of the ocean and the land. So we have a wide range of indicators of different aspects of the Earth system. But in each of these cases, as you can see, things are moving up and out of a long-term envelope of variability. So again, there's an enormous amount of data that sits behind this. But what we can say is that in each case, these are now outside the envelope of natural variability in the Holocene. And on top of that, we can say this excursion out is not driven by natural forces, it's driven by human activity. And there's a wealth of information to show that. So in summary, this is one of the pieces of evidence that says we are now in a new stratigraphic state of the Earth system. We're outside the envelope of variability. Jan presented an enormous amount of information on that yesterday. National Geographic tried to do this in a visual way, and they're very good at doing that. And so this was something they published in 2011. And what they tried to do was show this pressure of the human enterprise. So what they did was take a very simple identity that Paul Ehrlich and John Holdren produced in 1974, that the impact on the environment is an aggregate of the population, how many we are, affluence, which is an indicator for how much we consume, and technology. How do we produce the stuff we consume? And so with three variables here, you can produce a three-sided figure. Here's population, here is world GDP, and here is technology represented by patent applications. So what National Geographic did was to put 1900, that's that little tiny square you can see there, and there's 2011. The box is filled with stuff we consume, boats, airplanes, refrigerators, cars, stuff, okay? Now, I was an advisor on this figure, and they sent it off to me, and they said, what do you think of it? And I said, you missed the point. They said, what? I said, put in 1950. They hadn't done that. And so they argued with me. I said, well, you know, they thought it was going to be somewhere halfway up. Big deal. I said, put it in. And then they put it in, and they came back absolutely shocked. There's 1950, all right? So there's the first half of the 20th century, and there's basically the second half. That's the explosion we call the Great Acceleration in a visual format. Okay, so that's a very quick tour of Earth system and how it's being changed. I want to talk a little bit more now about the human dimensions of this and how people are reacting to this term of the Anthropocene, and then bring it back into an Earth system point of view. Obviously, the first use of the term in the contemporary era, as Jan pointed out yesterday, was by atmospheric chemist Paul Crutzen at an IGBP scientific committee meeting in the year 2000 in Mexico. And after he uttered that, there was obviously a lot of discussion around the room that this was a great way to pull together all sorts of stuff that was going on in the global change community at that time. So we encouraged him to put an article in the IGBP newsletter. So the meeting was actually in February 2000 in Mexico. So by May, we published this first use of the term in the contemporary era, Anthropocene. And as Paul pointed out, he said actually he scoured the literature and found it was actually used in the 1980s by an American biologist, ecologist, Eugene Stormer. And interestingly, Stormer agreed to have his name on here, but he was not at all interested in pursuing the idea any further. He just sort of dropped it. So it was left to Paul and the IGBP community to start using the term much more widely. But then Paul published basically the same stuff in a peer-reviewed journal in 2002 in Nature, where he explicitly proposed the Anthropocene as a new geological epoch. He used the word epoch. And he suggested then that the start date be set at the beginning of the Industrial Revolution, the late 1700s, recognizing, of course, as we heard from David, the enormous importance of fossil fuels in the whole history of humanity and history of the Earth. And of course, Paul recognized that straight away as well. Okay, where are we stratigraphically? Jan pointed this out yesterday, so I'll only briefly summarize. As Jan pointed out, we've got an enormous range now of stratigraphic signals that are being laid down, emerging, that are beyond the Holocene norms, and are going to leave a lasting record. I think the working group's done a fantastic job on that. Evidence is most consistent. The majority think a mid-20th century beginning, roughly around the beginning of the Great Acceleration, is probably the optimum, although there are differences of opinions on that. And there are a range of dates that have been proposed from 45 to 64. And as Colin Waters and the rest of us say, we've got some more work to do before we present this to the International Commission on Stratigraphy next year. So Jan gave a tremendous overview yesterday. I'm not going to talk any more about the stratigraphic side of this question. But I want to talk now about how other communities are reacting to this. And my colleague Catherine Richardson in Copenhagen actually makes a really good point. She says, science has a history of shocking humanity. We have Darwin there. And of course, he still shocks humanity in some parts of the world. They still don't accept this, despite the overwhelming evidence. And now we've got the Anthropocene. Can humanity really affect something so big as the Earth system that has this enormous, powerful dynamics with ice sheets and oceans and solar forcing and all this stuff? Can we really do that? And if we can, what are the implications for our definition of progress, our way of life? And that's where the rubber hits the road in terms of how people respond to it. So here are some responses. There is a notion out there that the Anthropocene is actually a good thing, and there's nothing unusual about it. Earl Ellis, a colleague of ours on the working group, and a number of his colleagues proposed that, well, this really isn't anything new. Humans have done this all along. This is just a continuation. And the Anthropocene really began thousands of years ago, basically with agriculture, with the Neolithic Revolution. And he says, well, we're in charge now, so let's make this a good Anthropocene. It's in our power now to as he says, the environment will be what we make of it. So that's one view of the Anthropocene. Quite a divergent view comes from historian Jacques Grunewald and philosopher Clive Hamilton. Clive's probably familiar to a lot of people here. And they say it's quite the opposite, that the idea of the Anthropocene is an absolute rupture in how we view the relationship of humanity and planet Earth. They argue that the age of man, the face of the Earth, the things that were discussed in the 1800s and early 1900s actually aren't a precursor to the Anthropocene. Their argument is it's only been in the last 20 or 30 years that the idea of the Earth system has come to the fore, that our planet is a complex system that is far more than the face of the Earth or imprint on the environment. And the global environment is not the same as the Earth system. So that's an important point they make. So they say this is a radical rupture with evolutionary ideas about the origin of the Anthropocene. And it dispels this notion of the good Anthropocene people that this is just a progressive and somewhat linear evolutionary trend of human development. So we have two very different views there. Dipesh Chakrabarty, another well-known historian, in his Tanner lectures earlier this year at Yale, made some really nice points. He was really saying, the issue we face now is that modern contemporary industrial humanity is based on a homocentric approach. It's all about us. How often do you hear people say, in the climate change issue, don't worry about the polar bears. It's not about the polar bears, despite that wonderful image we saw yesterday. It's not about the polar bears. It's about us. Dipesh says that's actually the wrong approach. He says we're part of something much bigger on this planet. We're part of life, a zoocentric approach. And he has some wonderful turns of phrase. And I just put two of them there. He says, we suffer from departmental thinking. Those of you who are in universities understand that really well. And it's really to the credit of the Big History initiative here that we're trying to get over this. But I love this phrase. He says what we need is epochal consciousness, which is a really nice way of saying we need to think that we're part of something much bigger than just humanity. So they're very, very different views coming out. And of course, the equity issue came out strongly in a paper by two Swedish social scientists who said, hey, listen, Crutzen and Stefan and all these people were really wrong to talk about mankind or humankind or humanity in general. And all these great acceleration graphs totally missed the point. They said the Anthropocene is not driven by humanity. It's driven by a segment that are hooked on this fossil fuel-driven, consumption-oriented, globalized economy. Of course, this is a strongly political science view of it. But they say that intra-species, intra-human inequities are part of this ecological crisis and cannot be ignored. So let's take that a little bit further because I think it's a common criticism of those of us who were working on the Anthropocene in the early days. These are two of those 12 graphs I showed you. So when you look at population from 1750 to the present, very steady but very slow increase in the wealthy countries. Almost all of the post-1950 populations come in the BRICS countries and the poorer countries. But when you look at real GDP, which consumption correlates really well with this, what you find is even with the rise of China, 3/4 of the consumption still occurs in OECD countries. They make a lot of stuff, but we're consuming it. So here's the figures. 18% of the population are here in the OECD, and we consume 74% of the world's stuff, and therefore impact on the Earth system. So this is the argument that people like Malm and Hornbory are making, is that we can't ignore this part of the equation. It's part of the Anthropocene. And the dilemma comes in here. And when I talk about inequality, I want to talk about it from a system perspective, not from a political perspective, but from an Earth system perspective. You see a curve developing here. Well, this graph shows imprint. Here we're using global footprint, imprint of human societies aggregated by country on the planet. There's one planet Earth, by the way, this broken line. So if you're below that, your country is on average consuming less than one planet Earth. If you're above it, you're consuming more. This is a human development index. So we want to be up here because we want a high level of human development, but we want to be below here. We don't want to consume more than we should. So here's the problem. Contemporary society has an extremely well-defined curve which misses the sustainable development quadrant. This is a systemic property of the system we've developed post-World War II. Here you see the poor African countries down here. They have a long way to go to get a good quality of life, but they're consuming far less than one planet Earth. Here you see the USA. This brown one's Australia, by the way, and the green ones are most of the European countries. So we're consuming far, far more than our fair share of planet Earth. So let's just take a look now at the wealthy countries who, according to this, have a high human development index. There was some absolutely brilliant work, I think, by the British epidemiologists, Richard Wilkinson and Kate Pickett, published a few years ago. You may have seen this book called The Spirit Level. So what they did is they looked only at the wealthy countries. So they said absolute poverty should not be an issue here. There's enough wealth in these countries for everyone to live well. But of course, everyone doesn't live well. So what they did is they looked at income inequality, difference between the highest few percent and lowest few percent in a wealthy country, and social problems. You can read what they are. They're typical problems of wealthy countries. What they found is quite striking. An extremely tight correlation between income inequality. When it's high, you got more social problems. And that seems to be a system property that goes beyond culture. There's an anomaly here, and that's the US, which may have some cultural issues because its social problems are even worse than they should be, given the income inequality in the US. But if you look at all the others, the ones you expect to be best are the Nordics and Japan. But notice that there are quite different cultures between the Nordics and Japan, but they get the same outcome based on income. There is a hypothesis, unproven yet, that this is an innate property of humans. It's in our genetic code. That we tolerate obvious differences in societies, but when differences in wealth and power get too large, it becomes dysfunctional. It's part of how we are wired. That needs to be tested further, but if that's true, it's a profound result. So here we are in 2015, and how does our Earth system look? All right, these are all photographs from this continent, all taken in the last 6 years, all extreme weather events, and in each case, we have good evidence that they're being influenced by climate change, by the fact that we're destabilizing the climate system. We go across the Pacific to the United States. Here we have a number of magazine covers from Time, other images about the recognition of social problems that afflict that country and increasingly reflecting other wealthy countries as well. So here we have, again, systemic problems of how we're tracking in the Earth system, destabilizing the biophysical world around us, running up against problems within societies as well. And you have to start thinking, what are the system-level issues that are behind this? Some of the most provocative hypotheses have been put forward by these two people. We heard about Naomi Klein yesterday, but also I wanted to put Thomas Piketty up there. Some of you may have read his book on capital in the 21st century. Now, it's really, really easy to immediately get into political and ideological arguments about what these two authors are saying. I don't want to do that. What I want to do is put an Earth system lens on this. And when I read these books, and I read a lot of books, these two stuck out as saying they're actually talking about systemic properties of how the Earth system operates, and I'm putting humans fully in as part of the Earth system. And I say that because in Naomi Klein's case, she's saying that it's an absolutely fundamental characteristic of a capitalist system that if you're in business, you have to keep expanding. And if you're in the fossil fuel business, you have to keep expanding. And if you run out of conventional resources, you have to go elsewhere. You have to go to the Liverpool Plains. You have to go to coal seam gas. You have to go to the tar sands. And now it's in our backyard. And so people are jacking up about it. But it's a systemic property, which now, of course, is playing out politically. Thomas Piketty's fascinating. It's the only economics book I've read that's actually a page-turner. I couldn't wait to get to the next page. Because based on observations, great, a scientist loves this. He's not putting forward his latest theory about how economics ought to work. He's saying, well, look, we've got a few hundred years of data in France, Germany, England, and Sweden. And we got in the 20th century many more countries, including Australia. And he actually makes the argument, again, it's the systemic property of capitalism that it grows inequality. It's not that people are bad. It's not that they're ill-meaning. It's a system property. And as an earth system scientist, I find this really attractive because it's based on the most parsimonious explanation of really solid data. So here we have a system that is generating problems on the social side and problems on the environmental side. So obviously both of these people are saying, well, let's not scrap the system, but it has to be much better regulated, changed, and so on, to fit with the Earth system and to fit with humanity in our innate nature. So this is how I think ideas like this can actually start informing Earth system science. Because here we have a common feature that is affecting both the natural and the human part of the planet. So the last part of my talk, I want to just hypothesize a little bit about where we might want to be going. Because people are talking about, well, the common narrative out there is, well, we just keep growing. We need economic growth. We'll become wealthier. We'll bring people out of poverty. We'll meet the SDGs. Things will be great. And then a lot of us biophysical scientists are saying, wait a minute, things couldn't be quite so rosy when you look at it from an Earth system perspective. So here are a few thoughts. I really love history, and I love going back to history. So whenever I get a question like this, I say, we might have been here before. Can we learn a little bit from how humanity has reacted to challenges in the past? One of the best syntheses has been done by Sverker Sahlén at the KTH in Stockholm and Paul Ward from the UK. And when they look at the big picture history, they say it hasn't been this nice, even progress. In fact, we might find a human history marked by crises, regime shifts, disasters, and constantly changing patterns of adjustments to limits and confines. And if we don't recognize this, we may be blind to the warning signals that we're hitting limits and confines that we need to adjust to, like humans have in the past. So now I want to go right back to some solid Earth system science and interpret what the Anthropocene might mean as we go forward. Here's our familiar graph. I showed you that before. So there's our glacial state. There's our interglacial state. Now I want to look at the other graphs too, and you've probably noticed what they are. That's CO2. And as Jan and others have pointed out, there's a really tight correlation here between carbon dioxide in the atmosphere and temperature. It's a complex feedback relationship that I won't go into in any detail. Methane, too, is another powerful greenhouse gas. Now, complex system science says, if you look at these three, there's something called a limit cycle here. And it looks like this. If you look at CO2, when it oscillates between these states, it is capped at the top and the bottom. It very, very closely stays to no less than 200 or 180, and it doesn't go much above 280. So between 180 and 280 is the natural limit of CO2 oscillation in the late Quaternary. We can see it, of course, for methane, and indeed, temperature is pretty well capped within a degree or so between ice ages and warm periods. By the way, the difference of these in global average is about 5 degrees between an ice age and a warm period. You see some polar amplification here. The difference is bigger at the poles. So where are we now? There's CO2. It's drawn to scale. So it's almost instantaneous on this temperature scale, and that's roughly 400 ppm. So we've really gone way outside the operating range of that complex system. We can do the same thing for methane. It's even farther out of the range. Here it is up here. And so you might want to say, well, what's happening to temperature? And now there's good evidence that we're outside the operating range at this stage of the Holocene. So these are the contemporary measurements since we've had enough on-ground in situ measurements to estimate a global average temperature. You can see from the last century it's been going up, and particularly since about 1970, it's been going up really, really strongly. Now again, we need to put this in a longer time frame to really understand what this means. So here's some work that was just published a year or two ago by the IGBP Pages project, which tries to look at global average land surface temperature over 2,000 years. So this goes back to the Roman Empire. And these are in 30-year averages. So if you go through this, you see there's a lot of natural variability here. And you can see maybe from about the middle of this record on, there's a very slight cooling trend. Here you see the Little Ice Age, which was discussed yesterday. By the way, there is no such thing as a global medieval warm period. It doesn't appear at all in here. That was a hemispheric phenomenon. It was actually cooler in the southern hemisphere while it was warmer in the north. And I always have a smile on my face when people like Tom say, don't forget the southern hemisphere, because all the northern hemisphere people jumping up and down and saying it was just as warm 1,000 years ago. Say, hey, what about the southern hemisphere? Well, they haven't even thought about it. So globally, there was no medieval warm period. But here we see the contemporary warming. These are the instrumental records put on top of the paleo records. They correspond pretty well, which, by the way, gives us some confidence in the fact that we're not doing a bad job using proxies here to estimate what land temperature was. So these are the projections from the IPCC, and they're now using a 2000 baseline. Now, when you look at this, you might not be too alarmed because those look like fairly smooth curves. But notice the temperature scale is far different from the other one, and the time scale is stretched way out. So what we see here is the best case scenario, RCP 2.6. We really get our act together, get emissions down, perhaps even learn how to pull some CO2 out of the atmosphere, and here's the worst case. So compared to 2005, this is only a temperature rise of about 1 degree, so that keeps us under 2. This is a temperature rise of about 4, so put on top of what's already occurred, this gets us close to a 5-degree world. And when you go up here, the upper range, it's looking pretty nasty. The point is, though, we want to put these on the same longer-term time frame so we can understand from an Earth system perspective what this might look like. So here's the graph I just showed you. Here's 2,000 years, and here's the temperature range here. This is in tenths of a degree. Now, to put those IPCC projections on, we need to go to about here. 2100 would lie about here. And we need to extend that up to 4 or 5 degrees at the worst case. So that's what it looks like when you map it on. So from an Earth system perspective, you would get really worried about what this means in terms of sustainability. Because compared to the 2,000-year period we've developed our contemporary civilization, compared to the natural variability our ecosystems, our agricultural systems, and so on are designed to cope with, this is an enormous shock. This is like a meteorite strike on planet Earth. So the best case scenario is probably around in here somewhere, and of course the worst case sits up here. So now we're up about here. We're up a bit higher. We're closer to 1 degree temperature rise. We're pretty much committed to 1.5 degrees to 2. Most scientists are extremely pessimistic that we'll hold it to 1 or 1.5 even. So even with a Herculean effort, we're probably looking at something around 2 degrees. Now, the argument from a sustainability point of view is that this worst case scenario, if the system gets out of control and goes up there, is really a collapse scenario. It's hard for me to imagine even a modern, highly technical civilization coping with a change of that rapidity and that magnitude. This is a big shift in the Earth system, and it's occurring at a very, very fast rate. So let's go back again and see, well, what does that actually look like back in time? It's interesting to go back to this graph and say, well, this is the world we've evolved in. Hominids have been around for here, fully modern humans just for those last 2 cycles. Well, it's interesting that we have now reached 400 ppm. Climate system is far, far from equilibrium yet. So what can the past tell us about what a 400 ppm world looks like? Well, the last time we were there was the Pliocene, here about 3 to 4 million years ago. And our best estimates were it was 2 to 3 degrees warmer than pre-industrial when the Earth comes to equilibrium, the Earth system. And it was 10 to 20 meters higher in sea level. Now, it may take a few millennia to get there, but that's a tough world for humans to live in, and that's where we are today. So if we go to a much higher world, or a 700, 800, or 900 ppm world, and a world that takes us to 4 or 5 degrees, there are other possibilities. Here, in this period, it was quite a bit warmer than the Pliocene, maybe 5 or 6 degrees. There was no northern hemisphere ice back in that time. Here, of course, is where the Antarctic ice sheets began to form. So we may still have some southern hemisphere ice, but no northern hemisphere ice. That's a vastly different world. And of course, could we even possibly go all the way back here where we had no polar ice at all, and it was a very much warmer world? You can see from here that this is a pretty stable state of the Earth system. It doesn't change very much. It takes a fair bit of knocking to get it back down into this state. So these are, from an Earth system's point of view, the question is not whether we go fractionally more than 2 or so. The question is, can we actually push the Earth system back into states that we know are stable? This first one here is interesting because the continental configuration is very similar to what it is today. It was, of course, increasingly different as you go back in time. Now, one of the things that could push us toward these different states isn't just the amount of CO2 that humans push into the atmosphere, it's internal feedbacks in the atmosphere, in the climate system, Earth system. These are what we call positive or reinforcing feedbacks. And there are a number of them that scientists have identified, which we have more or less some knowledge about. And they fall in 3 categories: melting of ice, changing ocean or atmospheric circulation, and loss of major biomes, major pieces of the biosphere. So what we're saying here conceptually is something like this, is that these subsystems of the Earth system sit in fairly stable states in the Holocene. And you can push them around like the ball in this little cup here, and not much happens to them as long as you don't push them too far. But as humans put more pressure on the system through emission of greenhouse gases, through deforestation, through putting phosphorus and nitrogen in great excess into the system and so on, we actually start eroding the depth of this cup like this. And we start knocking the ball up the side. And you may get to a point where the stability basin in the Holocene is flattened and you simply go to another state. And this can happen fairly suddenly. And you may be lulled into a bit of complacency because you don't seem to see a whole lot of change until you're near it happening. So let's go back and analyze what science is saying about some of these. Here's the Amazon rainforest. Here it's a combination of climate-driven warming and drying, plus human land use change. And what we've seen in the last 10 years is 2 very big droughts and associated fires, 2 events, single events, and they've undone 10 years of carbon uptake by the Amazon. This could be an early warning sign that if we push this farther, and models say that this could flip this century, we're going to lose a lot of above-ground carbon back into the atmosphere. Out of human control reinforces warming. If we look at the permafrost up in Siberia, we're getting sporadic outbreaks now at 1 degree of warming. Actually, it's more like 2 to 2.5 in the northern high latitudes. Estimates are that by 2100, we could lose from 50 to 250 billion tons of carbon. By comparison, human emissions are about 10 billion a year. So this is 5 years or 25 years of human emissions. Again, if this hits a tipping point, it gets out of our control. There's an interesting internal feedback in here called a compost bomb, and that's because as this dries out and warms, the reactions that take this reduced organic material and convert it into methane or CO2 are exothermic. They generate their own heat. So you have an internal heat mechanism as these reactions take off. So there's strong positive feedbacks in the northern high latitudes. Ice, this is Arctic sea ice. We're losing it at a very fast rate. Summer Arctic sea ice, faster than most of the models predict. And the polar ice sheets, the blue line here is Greenland. Again, you see loss, but you see that the rate of loss is increasing with time. This is classic behavior of a system that has a tipping point and pushing it toward a tipping point. And of course, these 2 are important for this one's important for sea level rise. This is important for albedo feedback, because as you take ice off the planet, whether it's ocean or land, you absorb more sunlight. That reinforces the warming. So scientists are aware of a number of reinforcing feedbacks. In fact, we know they were important in going from an ice age to a warm period. And the real scientific challenge now is we know the mechanisms, we don't know quite where, in terms of pressure, we're going to start tipping these. The point is, the bottom line is, the Earth does behave clearly as a complex system, which means we can't just decide that, all right, we've had enough, let's slow down the warming. Once we cross tipping points, we lose control of the system. and it's going to do what it wants to do. I can show you this very, very simply in this ball and cup model that we tend to use a lot in complex system science. So here we have the glacial interglacial cycling, we have the Holocene, we have the Ice Age. Holocene is a pretty stable interglacial state. When you look at the orbital forcing, which triggers this changes between ice ages and warm periods, we're actually not due for another glacial for 30 to 50,000 years. And that's due to the combination of orbital forcing. So with no human interference, this is going to be a long sweet spot for humanity. At least 30,000 years. André Bergier reckons it's closer to 50,000 years before we go into an ice age. So we can push this system and it stays pretty stable. But we know in the past that there are hot, ice-free or much less ice states of the Earth's system. So here we are in the Anthropocene. We are moving out of the Holocene envelope of variability. We know that really clearly. Jan put up a lot of data to show that that's the case. We're certainly headed not toward an ice age. If anything, we're headed toward a different state of the Earth system that's warmer and has less ice. But the question that we are debating in the Earth system science community is, how far can you push this before you really leave this Holocene basin of attraction? Should we be able to take pressure off the planet? And that's the question that we really face, is what really does this Anthropocene mean from an Earth system point of view? It could mean, if we keep pushing the system, that those tipping points I talked about are engaged, and we push the system to a much hotter state, very stable, and the Holocene actually becomes inaccessible. We can't get back to it. And in my view, societal collapse is very likely in that sort of scenario. That's a really tough world to live in. When you look at a 2 or 3 or 4 degree hotter world, some parts of the world, many parts of the world actually become uninhabitable because they're too hot for our physiology. We can't get rid of body heat fast enough unless we're in air-conditioned rooms. Or the optimistic scenario is, if we get our act together, cap warming at 2 degrees, take pressure off the biosphere, we could actually, over millennia, come back down into a Holocene-like state of the Earth system. And the jury's out on where we sit on that. And that is what we might call the sustainable future, or sustainability. So that's the question from an Earth system point of view that we're really talking about, is to remain in what we know is a sustainable state. We know we can thrive. We've got to keep some sort of conditions similar to the Holocene. The optimists would say, well, we're so technologically powerful, we can live in a very different state of the Earth system. But a lot of scientists aren't so sanguine about that. So the issue we face is that these series of tipping points I talked about just a few minutes ago probably add up to a planetary tipping point. Because we know that's so in the glacial interglacial cycling. We know when the 2 big feedbacks, ice albedo, greenhouse gas feedbacks, get going, they move the Earth to a new stable state. They don't stop halfway in between. So the whole idea now is to stay away from that tipping point, which is the whole purpose of the so-called planetary boundaries approach that some of you may have read about. It's not to solve local environmental problems or regional environmental problems. It's an Earth system approach to say, somewhere out there is a tipping point to a warmer world, and we want to stay away from it. So, just to summarize, this is our state of affairs, long-term variability of Holocene climate. The argument I'm making is, if we kept warming around 2 degrees or so, over a long period of time, the negative feedbacks, the uptake of carbon by land and ocean, may bring us back down toward a Holocene-like state. It's not going to happen instantly, but there is evidence that we could stay in this regime where we can exist and be sustainable. But somewhere there's a tipping point, and if we go over that, we may transition to a stable and much hotter state of the Earth system. So I want to close with going back to what Dipesh was talking about, a homocentric or a zoocentric view of our place in planet Earth. And I want to go back to something that Tom Griffith said yesterday, which I think was really important, is that for those of us who are from Australia, every time we go to a meeting, it's opened by an acknowledgement of country and traditional owners. And that's become sort of a mantra that we just say, and then we go on to the meeting. But Tom pointed out it should be far more significant than that we have the oldest continuously living culture on Earth, on this continent, And perhaps they may have some insights about what it is like to live on planet Earth for a very long period of time. After all, they came here during the depths of an ice age. They went through the last glacial maximum, which was a really tough time for many people. Came out through the Holocene. And as Tom pointed out and many others, they weren't static. They were developing, learning how to live with this continent. But they were learning how to live for a long period of time. And I think it's captured very well by Vilma Webb, one of the elders from WA. And she said it, in fact, she really understood biogeochemistry. Look at what she said. We're here for a short amount of time to do what we're put here to do. Zoocentric view, by the way, which is to look after country. Not to become wealthy. It's not all about us. It's to look after the country. We're only a tool in the cycle of things. There comes the Earth system, biogeochemistry. They actually understood it. We go out into the world and help keep the balance of nature. It's a big cycle of living. There it is again. Big cycle of living with the land and then eventually going back to it. So here is an indigenous culture that has an understanding of the Earth system. Interesting. Anyway, we've got some big challenges ahead of us in the 21st century. Thanks very much for the opportunity to talk to you. I'm going to stop there and hopefully we have time for some questions. I'm doing my usual Earth system physical scientist thing of talking about humanity as a whole. And increasingly you are becoming we, if you see what's happening in Paris. We have differences, but we're all on the same platform on that. And as the big developing countries develop further, they're looking more like we. But I fully acknowledge that there are huge differences yet in humans. But on something as fundamental as this, we have to learn that we have to be a we in one way or another. We got a long way to go, I think. In the world of 2050, I think we've got more power than I, as an old white male, think we have. I say that because our CEO, Amanda McKenzie, is extremely cluey about using social media and other forms of getting messages around. We live in a vastly different world of communication that the younger generations are really cluey about. And I think that's eroding some of the traditional power structures. Naomi Klein made this point really well, and I saw her book launch of the Swedish version in Stockholm recently, saying that, in her view, the only way we are going to solve this is have power coming up from large groups of people. The entrenched power blocks aren't going to solve it in her view. Other people have different points of view. So I think that's an open question. But I see some possibilities through working with the Climate Council that non-traditional ways of influencing a system can actually work. Clive Hamilton does agree with the Great Acceleration, the 1950 start date and so on. And he actually uses the Great Acceleration as evidence of the fact that this is a rupture between what we did in the past and the way we viewed things in the past and the way we're doing things now. So his sort of point of view is consistent with the 1950 date. But I agree with you on the other point, is I think you can step back and look at it from the big history point of view and indeed look at humans as a species. We scientists, natural scientists, love to do that. But we get called to account all the time by people who have different lenses, and quite appropriately. I think it was good criticism. The ocean absorbs an enormous amount. It's absorbing about 93% of the heat now, and probably will continue to absorb roughly around 90%. But I think the issues with that are possible rapid increasing stratification, which affects nutrients, which affects marine biospheres, and so on. Because we're land creatures, we tend to forget about all the rich dynamics in biosphere in the ocean, which are affected by rapid warming. Coral reefs are one that we in Australia ought to be aware of, because as the ocean warms and acidifies, they're going to be history, probably this century. So there are big changes occurring in the ocean. In terms of where I think that tipping point is, all the evidence I see is that we're reasonably safe below 2 degrees for most of them. In other words, the Holocene state of the Earth system is pretty resilient, but we're kicking it really hard, And I think if we go much above 2 degrees, I would expect to see more methane coming out of the permafrost. Amazon will be in trouble. Just the erosion of sinks on ocean and land. Remember, CO2 is less soluble in warmer ocean water. So the fact that the ocean's taking an enormous amount of heat out of the atmosphere is a good thing. It's got a kick in the tail because it means CO2 is less soluble in the ocean. So I think once you get up to 3 to 4 degrees, you're in the real red light danger zone of tipping out of the Holocene. I think they're very powerful in today's world and can be very disruptive. And at a point when you've got, if I now look at the human part of the Earth system, which seems to be exceptionally resilient toward the post-World War II fossil fuel-driven economy that we have, these sort of new digital technologies are really important in getting information out beyond the gateways that the powerful entrenched interests use. Yeah, the problem there is our governance systems at the time aren't really very well equipped to cope with planetary boundaries. And they immediately want to downscale it and say, what should my country do? And it's common in Europe. Sweden's attempted to do it. Switzerland's attempted to do it. We say, wait a minute, national boundaries actually don't fit into an Earth system point of view. We're talking about a single system. That's a point I made right at the beginning. The planetary boundaries are oriented toward that single system. Having said that, there's lumpiness at the less level down below that entire system. Like the Amazon basin is actually more important than the North American temperate forest from a system point of view. So the Amazon forest, although it sits primarily in Brazil, is sort of a universal part of the Earth system that's really important. Whereas you can forest and deforest and reforest temperate forests in Europe and North America, and you don't affect the Earth system very much. So it's very unfair in terms of how our politics is organized compared to how the system works. And one of the things we keep cautioning countries is, this is a paradigm shift. You can't simply downscale your boundary and say, by the fraction of population or fraction of land area, because that's not how the Earth system works. So we need governance systems, and the governance experts are grappling with this. Governance systems like a UNFCCC, which is attempting to say, hey, this is one climate system. And you see how the negotiations start breaking down very quickly into national interests, into wealthy versus poor, north versus south, all this sort of stuff. We got a long way to go, I think, before we can actually implement the planetary boundaries properly from a governance point of view for these reasons. Look, I would sort of say all of the above. And the reason I say that is we are facing a big systemic problem. So it shouldn't be isolated. So that's why I think the broader philosophical, fundamental moral issues that talking about how indigenous people relate to the land is just as important as the immediate action of, from a carbon budget point of view, you just simply have to get out of coal ASAP. From a scientific point of view, that's just a no-brainer. So I think it all fits together when you take this big picture of what the Anthropocene represents, even bigger picture that David talked about of where humanity is going, and these big transition points of agriculture and fossil fuels in the system, and now what science is saying, what we need to do from a scientific point of view to keep the system stable enough for us, but then all the other non-scientific issues that you were referring to that are actually really important in making all this happen. So I'd say all of the above are important.